In this new series, we're going to take a look at trigonometry. We're going to look at it initially from the pure math basis that you're probably learning now or have learned in middle or high school. It's really important to build that strong foundation that you understand all the fundamentals of trigonometry. But what's more important is when you go into engineering courses, how do you apply the trig functions? Now, it's sometimes hard for students because there's a bit of a gap in time after they've learned trigonometry and when they start taking engineering physics courses. So maybe this is a recap for you before you start taking these courses. The good thing is there are very fundamental things in trigonometry that are used over and over in engineering classes. So I'm going to focus on the fundamentals and think about different tricks that are used in many problems in engineering. You'll see certain patterns, you'll see certain forms of the trig concepts show up over and over. And so that's what we're going to focus on. So when we look at trigonometry from an engineering perspective, what are the key concepts that we want to be able to fully understand so we can apply it to physical systems? Well, trigonometry from a fundamental basis is a way for us to relate lengths to angles. So oftentimes we're introduced to a triangle and we're given the lengths and we're asked to solve for the angles, or we're given the angles and we're asked to solve for the lengths. Now, we can look at more complex geometries, right? And you could systematically break those down into small triangles as well. So the triangle is one of your fundamental tools when we're looking at trigonometry. I've also put lengths in quotes here because we can measure lengths with a ruler, right? We can measure 5 inches, we can measure 5 miles, we can measure physical lengths there. But trigonometry is useful beyond actual lengths. We can look at vectors, and in future series, we're going to look at vectors. And a vector, just to put it in context, in this video is just a way that we have a length, right? So with some kind of magnitude, so some number that represents the length of it, and a direction. So a physical length typically doesn't have a direction unless we put on an XY plot. But if I measure the length of this pen, I typically don't give it a direction. But if I push something, if I put a force, now I have a certain direction, the direction I'm pushing on, and then I have a magnitude, how hard I'm pushing on it, right? I'm sitting on a chair, so I'm pushing down on this chair. I'm putting a force on this chair. So force is a very common way to use trigonometry. All right, system like that is very simple. But what if we put a box on an incline? If I put a box on a flat surface, I know that the box is putting weight directly on that flat surface. If I put a box on an incline, I know that it's putting weight down, but how much of that is distributed in this direction? How much of it is distributed in this direction? We can look at that as a triangle essentially with a direction component, and these are all just forces. So this is the weight of the box pushing down. We can use that, and if you take in a physics course, this is a very common problem that you look at to determine how fast or how much the acceleration of the box is as it slides down if it's a completely frictionless surface. We can also look at systems. Common system is for statics. All right, statics is a form of physics where we look at, right, maybe something is hanging, maybe you have a block hanging from weights, right? So these are ropes and there's some mass here, but you can make it even more complex than this. So there's a whole bunch of different combinations where what is dependent on angles is not just a length component. It could be a force, it could be a velocity, right? We looked at the case where you have someone throwing a ball, and we know that follows a quadratic equation. But I can completely separate when the ball is here. I know that the velocity is in this direction, but I can completely separate and look at the component that is in the vertical direction and the component that's in the horizontal direction. So this is velocity. We can use trigonometry for. These are forces. And there's a whole bunch of other cases where you can also relate these. But it goes back to the fundamental of how do you relate the magnitude and the direction to the angles. Trigonometry will help us with that. You've learned about sine, cosine, and tangent, right? These are functions that when you first learn about trigonometry, either in was it middle school or high school, it can seem fairly arbitrary what these are. It seems kind of made up. But after you learn it, typically what I find students in my engineering class that they understand this concept, but mostly in one a setting. And it might be this triangle setting or might be an oscillation setting. But if you only understand it from one setting, you miss out on the combinations that gives these functions the true power and usefulness, right? So in addition to looking at it from a triangle perspective, and we'll see this in a future video, I like looking at sine and cosine terms in the context of a unit circle. So unit circle is a circle with a radius of 1. So that's why we call it a unit circle. And typically we define some theta or some angle from the x-axis counterclockwise. And so we can use this to describe and help us remember what sine and cosine are. And then from that, we can build what the tangent term is. In addition, systems with oscillation, right? So we can look at sine not only from a angle and a length scale ratio, we can also look at it from an oscillation perspective. We can look at cosine from that perspective. We can look at tangent from that perspective. And we can look at the combination of our sine, cosine, and tangent terms, how they relate. So what kind of systems oscillate? These are usually are considered ideal or force ideal systems. So very common ones are a mass spring, right? So if you have a mass and it's oscillating up and down, we can measure the location of this mass and we can plot it. And that can be plotted as either a sine or cosine, right? How large are these periods? What's the frequency? What's the amplitude? These are also common things. If I drop a ball, a bouncing ball, and it hits the floor and there's no air resistance and we're in this ideal system, that also is going to oscillate. So we can look at these kinds of systems and apply sine, cosine, and tangent terms to help us describe it. So you see these multiple ways that we can use trigonometry for a variety of parameters. So we'll take a look at all these different ways to use trigonometry in this next series.